All right, at the request of students, I'm here with Chris Hughes. We're going to step through the same type of SolidWorks instruction that I did in class yesterday, so that way you can pause it, record it, watch it in slow motion, whatever you need as a refresher to help you through the project. Keeping in mind from the very beginning that the FEA steps that I show you are just so you can get a notional idea of stress flow if you have no natural intuition of what's going on in the world. That's fine. We want to help train you in that. So, but please do not in any way consider yourselves ready to go out and perform professional FEA. After seeing this, it's just a tool to help you design at this level. Please take more classes and everything else. So, disclaimer over. The first thing to understand is that this wing OML that's been given to you, this is the download that you're seeing, is a surfaced part. If you go to split, which is the icon I just clicked on, you should change the plane through which it's actually cut. Let's use this plane, actually slide it up. You can see if I zoom in all the way inside the wing, there's no material. It's not a solid body. It's hollow. In fact, a surfaced body is a mathematically thin shape. There's no thickness. There's no mass. It's just a surface, as you might expect. This one happens to be completely watertight. Every edge on the surface is black. If it's an open edge, meaning they're not joined, it'll be replaced by a blue line. But all the black lines mean it's closed. That means you can go up here to the surfacing tab, which, since we're starting from a low level, if it's not there, right-click on any one of these other tabs, and you get the options of what to turn on and off. I mean, there's weldments, sheet metal, mold tools, lots of other toolbars you may have never messed with. Surfacing is one you can turn on and off quite readily. But on the surfacing tab, you can click thicken. You can click on the skin. By default, it's just going to try to actually apply this thickness to the whole skin, just like you're making it out of aluminum or something. So we can try that. 0.05 inch thickness. This is made for the bisecting the thickness, so both sides would be 0.05. We can see if it'll work. I have my doubts. It's trying. Thicken operation can be error prone. Good. Let's crash SolidWorks right first step. This will be wonderful. Something happened. I think it gave up. Yeah, it gave up. So just like the offset tool, the thicken tool can be problematic. Let's try just the inside, see if that one works. Well, because really the reason the offset and thicken are both problematic is that they're built on the same thing. Actually, I think that one went. We have one solid body now, so if we actually slice this again, you can see there's no longer just a mathematically thin surface. This has thickness. And don't be alarmed by the terrible polygons applied to this. That's just SolidWorks discretization of the truthfully smooth surface it's built. If it put 1,000,000 polys on this model, your graphics card would be so terribly taxed updating it that it wouldn't really work. If that really bothers you, I think you can go to what? Tools, Options. Where's Options? Maybe because I'm in this subset. There we go. Tools, Options, Graphics, Performance. Go to Image Quality. And you crank this all the way up to higher for shaded and draft, optimize edge length. We'll see if that does it. So now if we go back in and slice it, I think it's a little bit better. Yeah, it's better. It's not perfect, but it's better. So if you're trying to take a screenshot or something and that discretization is really bugging you, just rewind the video, look at the process I just clicked, and that's how you can make it look a bit prettier for some sort of section view. If you don't want the blue plane there, you can click OK, and then that actually temporarily slices the entity. You can undo it. That works on assemblies. It works on complex parts. It's really, really cool way to peel back layers of your models. So anyway, now we actually have a mask, but I don't want to do that. So thicken, delete, yes. You can also use the thicken tool to check the box and create a solid from that entire closed volume if it's watertight. If there's a hole, it's just not going to work. So we click OK, and that makes it completely solid, I think, this time. Yep, so you can see it's solid material through and through. I would not recommend milling this wing out of a solid block of aluminum. It would definitely hold the load, but it'd be way, way too heavy. So now, on to more meaningful activity. As you saw in class, or maybe as you're seeing here for the first time, we are going to create a sketch normal to the top. It's basically a top-down planform view of the wing. In fact, in this case, I'll create a distinct center line going right from the middle of the wing up, so that way I can just mirror all the activity I conduct on one side over to the other. And again, another efficiency measure, I'm going to be a bit more intelligent about how I draw these lines and just use a pattern. We'll do 1.5" rib spacing. That's a complete guess. Maybe your method of spacing those will be a bit more sophisticated. And then I'll do a linear sketch pattern in the some direction. It'll be fine. We'll choose this entity. Spacing right now is 0.1 inches. No, let's try 1.5. Sounds good. We need more than 2 of them. Wow, that's not enough. I need to, yeah. That's too many ribs. 2 inches. Done. Okay. The end spacing is not beautiful, but that's okay. We'll create those. And then I will manually come out here and create 1 rib close to the end. Now this is an interesting rib, because if you put the line straight on the end cap, and you thicken it, then part of the solid surface is going to be inside the body, so part of it's going to be out. So we know that we have 3/32 of an inch thick balsa, so I'm going to go ahead and dimension this as 3/32 of an inch away from the actual tip. Come on. Come on. We'll try again. From here to here. Good. That's nice. How about we use a point to there? Right. I told you SolidWorks. You were going to do it one way or the other. All right, there we go. 3/32 of an inch. So that way, no matter which direction the rib is extruded, it is going to work. So we have probably too many ribs, but it's only going to sacrifice a few grams of weight. Might as well go with it. Notice each one of these lines extends well beyond the outer mold. What? No, the outer mold line of the model. So I think that'll be good for the ribs. We'll accept, and then the next step in that is to go to Features, Extrude. It already had that sketch selected. If it didn't, you can always go in the tree here and set the sketch. Notice by default it has thin feature selected here. Instead of one direction of extrusion, which notice it's going in one direction away from the sketch. We want 3/32 because I'm working in IPS, so it'll be default to inches. I'll do mid-plane, sure. And instead of just being 0.1 inches tall, let's do something extreme, making sure it goes all the way through the wings. That's a little bit much. We can drag that down, and that will be sufficient. That passes through with plenty of margin. No errors here for being sloppy. So that looks kind of weird, but it's okay. Now to give you a preview of the magical step we'll do when everything is put together, we'll go to Surfaces, do Cut with Surface, select the surface that's going to be the knife cutting things. We look for the arrow, which in this example exists here. It's going to remove material on the side the arrow is pointing. So right now it'll remove all of the solid material on the inside of the wing. We'll flip that arrow, click OK, hope it all works out. In this case it did. Because now we see that all the solids have been trimmed down to the inside of that surface body. We can go in here to the list of solid bodies, surface bodies. If we hide the surface, then there are all our ribs. You could right now export that to DXF, to a laser cutter. You can. Well, I'll show you that later. Make a note of that. Export. But establishing these two-dimensional surfaces, well, ish two-dimensional, is what you're targeting for creation of G-code for a pattern to actually cut material. Keep in mind that this surface is still actually slanted. If you zoomed in there, you can actually find that this wing is contracting as it goes out towards the tip. So these are not pure two-dimensional shapes. If you view it from the very end, not that one, there we go, you can see that even for an individual rib, you see two lines. So you see some projection of that surface as it's slanted. The laser cutter is not going to do that for you. You're going to have to pick, probably I would say, the smaller side to put into the DXF because it'll be more compliant with the actual OML. So just be aware of that. You are being more precise than the actual ribs in the end will be. In circumstances where you had extreme contraction, you actually wanted to have a rib include a contour, you would have to CNC machine that rib out, probably with multi-vertical passes, so that would actually put that contour inside the rib structure, and it works. I've done that on at least one UAV. It just takes a little bit more time. Okay, so those are ribs. Let's show the OML again, and let's keep adding some parts to it. In fact, I'm going to go back in time before the surface cut. We'll show you how we can do some black and magicry with SolidWorks. So right plane, vertical top view, okay. Let's put the spar in. It doesn't have to be terribly fancy. In fact, we need to put another center line so I can make sure everything's sitting lined up. Notice I'm taking advantage of the fact SolidWorks will let you latch to a midpoint automatically. Sounds good. The spar, you could go through here and measure the exact quarter cord, but yeah. Notice because it's tapered, this actually has a forward swept quarter cord. So it's a little bit structurally unstable if you want to look at it that way, but you could justify putting the quarter cord there, you could justify putting it back here, you could justify not even making it straight, and you could keep it at the exact quarter cord of the wing, which probably looks something like that-ish. But I'm going to go horizontal. Okay. So that extends a long way that way. Let's put another spar back here. This one is going to be slanted. In fact, I want to get it right inboard of that control surface, because in reality you'd want those hinges and the connections to be attached to something. Yeah, let's do that. So a thin extrusion, same as before, one direction, 50 inches tall. You change that to actually mid-plane. That'll be sufficient. Now we have one more sketch to make, which will be our solids. So these are no longer going to be thin extrusions. Last time I need to do a center line going up from the middle. The best thing to do is set up a center line plane. If I had drawn this model a little bit better, it's actually drawn on top of the 3D printed part, the STL file, so that's my excuse. But if I drawn this better, the triad of planes would overlap on the mid-plane, the water line, and the butt line of the aircraft. So this solid region sketch there is going to become the leading edge stock, and then actually do this with a different line. The trailing edge stock, meaning the solid portion that makes up the back side of the wing, we will trim out of a solid line that looks like that-ish. Same way, we'll go ahead and extrude this as a solid. The nice thing about this whole process and this method is that you can make this out of super, super simple shapes. I mean, these are blocks. And so, yeah, all right, we'll go with that for now. We'll go forward, and you notice it, oh, it actually did cut everything. That's wonderful. There's one downside, one thing I have forgotten to show you at this point. Even though we can undo this and hide the surface, it's cool. It looks awesome. That's a very simple way of making structure, but the problem is, as you would like to separate this leading edge stock away from the rest of the parts to make G-code and go machine that on a CNC machine so it matches perfectly. That'll be a wonderful leading edge device for you. You notice it's all combined into one part. Whoops, forgot to check a box. So if we go back into the parts, we can now describe how you do multi-body single parts. If you uncheck the merge box there, it should fix the problem, right? Created some other problems. That's okay. We'll fix that too. These need to probably also be unchecked. Oh, it already is. But this last operation, each extrusion will try to merge everything. So, okay, now we've really made a mess of things. We need to modify the surface cut. Okay, instead of just being the selected bodies that you're going to be cutting, let's cut all the bodies, and we'll keep all the bodies. There we go. So now these are all separate parts. You could take that inboard rib, right-click, insert a new part, and you can save it off in a part by itself if you wanted to. That would be its own solid body. That would be very, very useful to do for the leading edge stock, which is apparently surface cut 13. You can say right-click, insert a new part, file name, leading edge, save, okay. And there you go. You have a part of just that leading edge, which now this is very easy to do computer-aided manufacturing operations on, and actually take that to a CNC machine and cut out. So that's one way to go about that. But each one of these parts is isolated. It would be nice at this point if you could essentially make a slot for your shear web to remain uninterrupted. The ribs are by far a much more lightly loaded structure than the actual main spar. In fact, the leading edge stock you may not want to be terribly structural either, or maybe that also becomes your main spar. Your choice, your design, whatever. That could be foam for all I know. I need to show you a tool called Indent. So this is not actually on the toolbar by default. So you go to Insert, Features. First, I'll show you the more traditional kind of CATIA V4 method. You go to Combine, and these are Boolean operations. So even to subtract, you have to go to the Combine tool, but it's just where you're taking one solid body out of another. It's kind of the more traditional style of CAD design before you had some of this automated joining and stuff. But we can, in this case, subtract. The main body would be the rib. Bodies to subtract, want to subtract out where the spar crosses through. You can do a preview, and that's going to show you that it's actually used the main shear web, the main web of the main spar, as a solid body to subtract out of the rib. Now in this case, it's very simple. It's just a plain cut. But Boolean operations are very robust for even extraordinarily complex shapes. You can take a solid body of an aircraft and subtract it out of a block of material to make a mold cavity. It can be very, very complicated, and Boolean operations still work quite reliably. So you can say okay and keep it, but the problem is that operation now consumed the shear web. So that's not exactly the outcome we wanted. I'll undo that operation. We're back to where we were before. I'll show you the other tool. Like the other thing worth showing here is if you do have a bunch of different bodies you want to combine, you can change that to add. Select everything, -1, perhaps that you don't want to add. That was control that I unselected that with. Click OK. It does some maths, and now you have 2 bodies remaining. You just have the leading edge, and you have the rest of them. So you can use Boolean operations to combine multi-body parts relatively easily as well. Undo, all separate. OK. Insert features. Indent is actually more useful for a lot of aerospace applications and part making than cut, which is kind of weird. The target body here I want is, again, the rib. The tool body be the spar. I want to remove the selections. It'll be a cut. Okay, so it's giving me a preview. I think that's right. It appears to be right. So now we have the aft portion of the rib and the front portion. Good. The problem is you'd have to do a lot of indent operations to do this for every rib. So have fun. But it's the same thing over and over. It's reasonable. The other option, keep in mind that if you did just laser cut these, you could just use an X-Acto blade and slice out the contour. For something as simple, you still have capabilities built into yourself. So that's indent. Multi-body, we've done cut with surface. I'm going down my list of things I need to show you. Boolean, add, subtract, indent. Materials. So if we wanted to apply a material to this part, in fact, yeah, it's time to switch over to my other cooking show part. Nope, not the leading edge. The sample wing. This is the part that was kind of made. It was produced from last year's project definition where they built a 48-inch wing that had to be cantilevered out from a single point mount. So I'm going to initially modify this to kind of break it. Those of you who saw it in class will remember this change. But here we go. So that makes it a much worse structural design. But I will go ahead and assign a material to this part. Right now it says material not specified. You can right click and either select from your favorites, or you can say edit material. And you can select from the list. Steels, irons, aluminums, it has quite the built-in categories. But underneath wood, you can select balsa, which is fine unless these material properties are not exactly what you got out of the box. Balsa is obviously an organic material. It's going to have variability between sheets, between trees, between companies, between regions of the plant. It's just going to be different places. So do you have a different yield strength? We don't even know tensile strength. Do you have the same Poisson's ratio as something else? There's a reason not many of the wood properties are populated in SolidWorks. They don't want to be susceptible for those issues. So as you're starting out, if we're going to run an FEA study just for insight of stress flow, I would encourage you to use something basic, perhaps a plastic, like I think we did ABS polycarbonate, acrylic, sure that's clear. Or you can even go into use an aluminum, just some sort of isotropic material that doesn't have the directionality considerations, so you can do a basic stress flow analysis. So apply that material, look at it, even applies the visual properties, and you're pretty well set on that. So that's how you can go about setting material, which now the nice thing is you can go to the Evaluate tab, click Mass Properties, and it tells you the weight, the volume, the density, everything of the part. If you had multiple bodies, each of which had a different material, a different density, it will accurately calculate the mass moment of inertia of the entire system. It will accurately give you the overall mass and the center of gravity of that entire system, even with different materials. You can define custom materials if you feel like it. So definitely a thing worth doing. So that's mass properties. Of course, the other thing is you can go to section properties, which if you select a surface, well, Okay. I don't want the whole solid parts. We just want one of the surfaces. That particular surface you can now recalculate, and it gives you the area properties. Not terribly significant for that selected area, but for perhaps just your main spar calculations or some sort of inertial calculations, that's a useful tool to know where it's at. So it's section and mass properties, not a bad thing to do. Okay, so now just to step through a simple FEA study, you need to make sure that you go into Tools, Add-ins, and check SOLIDWORKS Simulation. If you don't see SOLIDWORKS Simulation, that means you probably have the Student Engineering Kit, which does not include a lot of these extras. You also will not see Flow Simulation as a possibility, though all the AME labs should contain both SOLIDWORKS Simulation and Flow Simulation. So if we click All Right, you can then go to the Simulation tab. We'll do a new study. As I said, there's lots of different options we covered in class that we'll start in FEA as a static study, but you can also do thermal analysis, looking at flow of heat. You can look at stresses arising due to thermal effects. You look at natural frequencies of a mechanical object, buckling analyses, drop tests actually does an impact load. Just lots of different numerical studies are possible, up to and including fully nonlinear, like physics-based simulation with gravity and everything else. It's pretty neat. That stuff takes a long time to calculate, but let's definitely walk before you try to run inside of SOLIDWORKS. So static analysis, we'll say OK. This brings up the familiar menu. We need to see that we right now have two bodies included. There's one surfaced body and one solid body. It's going to try right now to do math on both of them, but let's exclude the surface body. Exclude from analysis. So it still exists. We're not deleting anything. It's just going to be ignored in terms of FEA. On the solid body, you see that it brings in the material, acrylic, medium, high impact. If those material properties are right for what you're doing, fine. I would not recommend at all building your aerospace structures wing out of acrylic. It'd look really neat as it shattered. So anyway, fixtures. Let's apply some fixed geometry. These are basically one of the types of boundary conditions you apply to finite elements analysis. This is modeling like if you had just glued that stick into a mount permanently. Those surfaces mathematically will not move. There will be zero deflection on every one of the nodes forever and ever. Cool. That end condition in reality probably doesn't exist, with the exception of bonding it into a perfectly machined whole. External loads, like lift. Lift could be defined as a pressure or a force, but just from doing this a few times in both methods, I found that force is better because it allows you to select an entire face, which now in this case, all of the ribs, we're going to be assuming that the microlite, the monocoat, the plastic coating of the wing, does a decent job of transferring the load into all of these discrete surfaces. So the total load in our case, I think it at 45 in class is way too much. Let's do 20 pounds. You'll be able to determine your required load from the project definition. So 20 pounds per item. Right now it makes a difference if it's total or per item because they're the same thing. Then we could go up here and select the top surface too, and then we'd have to do the total force. You can kind of see now which direction it's pushing. In fact, we want to do a selected direction, not just normal to the surface. I'll select that vector direction, or you can also use a plane. We normal to plane. There we go. So that's the direction we want the load to be in, the lift direction. This will be applying basically load to the bottom and the top, which I don't like, so let's get rid of phase 2. Actually, it's not a bad approximation. Lift does act on both top and bottom. In fact, if you really wanted to be accurate, you'd have to map the pressure distribution over the entire airfoil on here, which you can do, but we're not going to get into that right now. All right. English, 20 pounds force. I think we're good. That's the load. Now this is the part where, as I alluded to, professional stress engineers hang their head. If you go to the mesh, you could right now just click run this study and we'll see if it works. It crashed the first time in class. Yeah. So the mesh default settings failed, which is not terribly surprising given how small some of these parts are. So we right click on mesh, we'll have to create a little bit of finicky mesh, and that slider is convenient, but gosh, it's an oversimplification. So we want to go down to, I think to get this work in the past, I'd use a curvature-based mesh, which will start applying more and more cells as a surface becomes more and more curved. Let's do 0.2 inches as the maximum size. Notice it automatically resizes the smallest. Number of elements in a circle. Okay, so that's the scaling. That should be plenty enough to get this thing going. Let's see here. Generates the mesh. Come on. Got it. All right. So this shows you kind of the level of mesh you're dealing with. It's still probably way too coarse for an excellent study. Just for kicks, let's do one that's way smaller. So instead of 0.2 max size, let's do 0.05. That might be on, yeah. It should take much longer to generate. It'll definitely take longer to solve. As you notice, doing these type of operations will completely chew up RAM. Told you it'd take longer. Just have some music. Chris, you want to sing a song? He said no. Almost there. So if the mesh alone is taking this long to solve, imagine how long it's going to take to solve a solution based on it. So, but I want to show you what the tiny little elements look like. Hey, look, we're in a gig of RAM now. Oh, there we go. Come on. It's thinking. There we are. That's, yeah, I overdid it. That would probably give you a valid solution. It's going to take you a while to solve. Now, it is a mesh that's able to give a valid solution. Your structure could still be terrible, and it could still break. But if your structure is viable, this may be a reasonable mesh. Of course, the only way to tell is to try it with a smaller mesh and a more dense mesh, and then you can do a grid convergence study. So, enough elements when you zoom out, it just looks like black nodes. Let's not run that because I don't want this video to be 4 hours long. We'll create a simpler mesh, go back down to 0.2. That should be much quicker to solve. Yeah. So, but also you see the resolution is just smaller. So that's the decision you have, and that certainly does affect the quality of your final solution. So now we can run the study given the boundary conditions, the loads, the mesh we have. This is actually going through the process of solving. This basically is telling us that something is broken. Not in the solver, but probably in our design. Excessive displacements were calculated. It knows when the material is going past its yielding strain. So this means something probably broke on the model. Click yes to solve with a large displacement flag activated. Click no to solve with small displacement linear model. You can do yes, it becomes iterative. If you click yes, you have to actually, if you ever want to go back to the no option, you have to go back into properties of the design study and click no. So the first few times you run something, click no, it'll give you the quick linear solution, which in this case, yes, it completely breaks. 3.36 times 10 to the 8th, that's pascals, but we can change that. So right click, edit definition, change it back to American units. PSI, okay, so that's what, 48,000 PSI and something made of acrylic. Yeah, it's broken a long time ago. But as you expect, you see a massive stress concentration. One cell is exploding right there towards the top and bottom of this sharp corner. If you envision the stress flow that's going out from this solid mount that's inflexible, because keep in mind it's all constrained, it has to turn this corner through the rib and then turn another corner into the spar. You see, yeah, it's completely broken in the first rib. It's just not going to work, period. What's really nice about incorporating this type of activity all into one piece of software is that now I can go back to this original extrusion that's creating that stick, tell it to go up to direction 2, up to surface. Let's go out to the third rib. Why not? That gives us 3 ribs anchoring. Let's go back to the static load analysis. Okay, we have the loads, we have the fixtures. Let's just run it again. Notice it's remeshing because SolidWorks detected that the geometry has changed, so it generated a new mesh. Now it's actually solving the solution. These used to be steps you'd have to open up different programs to do. No, stay with the linear solver for now. I know my design is terrible. Thank you, SolidWorks. And this is what's happened. So what's very interesting is that you see, okay, the mount is unstressed because everything's magically numerically constrained. That's unrealistic. You can see that the load is actually staying mostly in this central spar through the first gap of the ribs, and then you formed enough of a couple with these other rib connections to the fore and aft spar that now you've seemingly effectively transfer that load out to the spars. But it's interesting that the main tallest spar is virtually unloaded here at the root. So now the stresses are down in like the 7,000 range, so that's more reasonable. Even maybe a plastic wing could withstand this. But of course, we've only applied a 20-pound load. This is also telling us that torsionally, our wing is a terrible, horrible, awful design. The wing is twisting far too much. It's deflecting in lift, probably a little excessively, but we want to, in the end, move that aft spar up, which, hey, maybe we can do that. I'm kind of curious. Okay, so that's this extrusion that does that. Let's edit the sketch. Go to the vertical view. Let's just move this up. Click OK. That was easier than I thought it'd be. All right, run the study. It's going to remesh. It's going to recalculate. Oh, come back. It's telling me there's still large displacements. Okay. But see, look at the difference that makes in total twist, total deformation. You now have a taller inertial section in the back. And this is just, again, giving you insight to where stress is occurring inside of a wing. You notice these leading edge ribs sections are not stressed up at all. The trailing edge is not stressed up significantly at all. That means you don't want to make those parts out of aluminum. You don't want to put a lot of your high weight, high cost materials there. But you see that the shear that arises inside of these central box sections of the wing, they can be significant. Now, keep in mind this is von Mises stress. You can read up that on your own real quick, or you can wait till we get to that description in class. But this should be a sufficient crash course in how to use FEA to better understand stress flow in structures. Do not, absolutely, after just watching this video, go out and do anything for real in industry. That'd be a terrible engineering choice. But this, for an educational purpose, hopefully will help you out. So, right, that's FEA. The last thing I want to show you how to do is actually back in the other model. If you wanted to take this rib section and actually export that to a file that you can laser cut, you right click, export to DXF DWG, that you can save one. Yeah, homework, sure, save. Entities to export, face 1, this face, and this face, and this face. You can select all of the solid. Oh, they have to be parallel. Okay, sure. All these different faces you want to export. Click OK. It should give you a oh. Well, that's unfortunate. Apparently, it's going to be one face at a time. But you can go out, and this is one way to export that. Of course, the other way to make a DXF of all the faces you need is to make an actual drawing from the part. You could actually import views of each individual rib. You could save each individual rib as a part and then drop them all into the same drawing. And keep in mind, those drawing files update as your part itself does. If you want to add lightning holes or take them out or whatever, the drawing files update along with it. So becoming proficient with SolidWorks, becoming proficient with any CAD program. It's just SolidWorks happens to be the one we have on campus and the one I like teaching from. Certainly saves you a lot of time. So you basically would export that as a face. That's what you get. Save. There you go. Now you'd have a DXF that you can actually load into a laser cutter and cut that part exactly to the shape and dimensions you see in CAD. The other way is to just print it onto paper, glue the paper down to a stick of balsa, and cut it out with an X-Acto knife. You don't have to have a laser cutter to build wings. People were doing this in the 1910s, 1940s. I mean, RC wings have been built for a while. So, Chris, anything else I didn't cover? You set? All right, we're done.